Good morning. My name is Emanuel Casiano Diaz, and I am a physics PhD student at the University of Tennessee, Knoxville. Today, I will be talking and presenting our results for operationally accessible entanglement in the Bose-Hubbard model. First, let me thank my collaborators in this project, Professors Chris Herman from Middlebury College, and my advisor, Adrian Del Maestro at University of Tennessee, Knoxville. A quantum many-body system is entangled if its constituents are non-classically correlated. For this project, we will be looking at the entanglement between spatial subregions of a system. To quantify entanglement, we will be using the Renyi entanglement entropy, which is this expression at the bottom, where alpha is a number and rho A is the reduced density matrix of subregion A, which has been obtained by building the full density matrix of the system, which is this outer product, and then taking the partial trace with respect to the other subregion, which in this case is B. Rho A will contain the probabilities of obtaining the different configurations in A. There's a little caveat with this quantity, this Renyi entanglement entropy, and it is that it contains fluctuations, it contains contributions due to particle number fluctuations. Specifically, it is known that the Shannon entropy, which is this expression here, of the local particle number distribution makes up this contribution. Here, by local, I just mean in the subregion A. So this is just the probabilities of measuring the different particle numbers in subregion A. The issue is that these contributions due to particle number fluctuations are not physically accessible as a resource for quantum information processing, and this is due to particle number conservation. So instead, the quantity that one uses, if you want to know what is the maximum amount of entanglement that we can transfer to a resource for quantum information processing, which is the accessible entanglement entropy. Here again, alpha is just a number, but notice that now instead of working with rho A, we actually work with a reduced density matrix that has been projected into the basis of fixed local particle number in the A subregion. And consequentially, this also fixes the particle number in the B subregion. So can we investigate how the accessible entanglement scales for a lattice of itinerant bosons? The model we will be investigating will be the Bose-Hubbard model, where here T, U, and mu are tunable parameters corresponding to the tunneling rate, repulsive interaction potential, and the chemical potential. B dagger and B create and annihilate a boson on the site, and N counts the number of particles in the site. This model has two phases: the superfluid phase at very low interaction strength, in which the bosons are non-localized, and at high interaction strengths, the bosons try to get as far away from each other, and we are in the mod phase. The exact value for this phase transition is 3.3, and I would just like to mention one of my favorite examples for our realization of this model in the lab. And basically, it's an optical lattice of rubidium-87 atoms. In this reference, actually, they even computed the full entanglement entropy, and the results were in good agreement with what you would expect from the Bose-Hubbard model. In our case, though, we will be performing a computer simulation to compute this. Specifically, we will be computing a lattice path integral ground state Monte Carlo simulation. The original algorithm was not for the ground state. So basically, I guess our contribution, and we talked about this in last year's March meeting, was basically extending this lattice path integral Monte Carlo method to the ground state. In this method, there's no access to the reduced density matrix of A. So instead, what we do is the following. We can rewrite trace of rho A squared, which is a quantity on which the entanglement entropy depends on, as an expectation value of the swap operator in the A subregion. Here we have a cartoon of how the swap operator acts on a system. So essentially you have the A subregion of a system and the A subregion of a replica. If we act with the swap operator, we just exchange the states of the system with the A state of the replica. And we can extend this trick where we rewrite trace of rho A squared as an expectation value to the accessible entanglement entropy, which is what we will be computing. For inspiration, we have this plot here. So actually, this is not from our code. This is exact diagonalization results obtained in the reference above, by some of our collaborators. And this is the accessible entanglement as a function of interaction strength. Notice that near the phase transition between superfluid and mod phases, there seems to be some trend. The peak of the accessible entanglement seems to be moving closer and closer to the exact value of the phase transition. At least that's what it looks like to the naked eye. So what we will do is the following. Let's fix the value of the interaction strength to 3.3, which is the exact value of the phase transition, and compute the accessible entanglement as a function of capital L, which here, that's just the total number of sites. In the following examples, we will just be working in a unit filling. So essentially, the total number of sites will be equal to the total number of particles. With our new algorithm, notice that we can obtain much larger systems than those that were obtained with exact diagonalization. So here, the gray line denotes ED results, and the limit is about 20 sites. Whereas here, we have at the very least 64 sites and 64 particles. We would like to fill this plot in a little bit more, generate more data points, so we can obtain some results for this scaling. Another interesting question would be, okay, so can we, instead of varying the total system size, can we keep the system size fixed, but study the dependence on the length of the subregion, which is the little l? Notice that we start to see some scaling, but then at the end it plateaus, and this is due to finite size effects. And think about how this lattice is actually subject to periodic boundary conditions. So we are essentially working with a ring. So perhaps it is more appropriate to calculate the dependence of accessible entanglement on the chord length instead, which is this expression in the x-axis. And indeed, you can see that we got rid of that plateau due to finite size effects. Other than that, the plot looks more or less the same. And for the first time ever, as far as I know, we obtain scaling results for the accessible entanglement, which were not possible before because it was just too expensive. In the case of exact diagonalization, it's just too memory consuming. So now we have some result here that the accessible entanglement goes as 0.4 times log of the chord length. So this is great, very exciting. And in the future, we would actually like to formalize the scaling forms for the accessible entanglement. So recall that for the plot in which we compute the accessible entanglement as a function of total system size, we still want to generate more data before we claim, aha, we found scaling results. Not only that, but we would also like to look at the accessible entanglement at higher dimensions. With that being said, thank you very much for your attention.